Theorem of Fractalplicitive Tachyon Detection with Fractalplicitive Inverse Theory. Statement: let E of t sub n represent the energy of a hypothetical tachyon at recursive fractalplicitive time intervals, t sub n, and let S of t sub n denote its spatial displacement. Under the assumptions of fractalplicitive time theory and fractalplicitive inverse theory, a tachyon may be detected if the recursive sequences of energy and spatial displacement exhibit both direct and inverse fractal scaling across time and space. This theorem is governed by the following conditions. 1. Fractalplicitive time progression. Time progresses non-linearly in recursive intervals t sub n such that each interval t sub nn scales by a fractalplicitive factor, delta of an, dependent on nt sub n equals t sub n minus 1 plus delta of n times t sub n minus 1, where delta of n equals gamma to the power of n with gamma as a constant fractal factor. 2. Fractalplicitive energy equation with inverse scaling. The tachyon's energy E of t sub n at each recursive interval t sub n follows a fractalplicitive relation incorporating an inverse fractalplicitive scaling factor h of n that scales inversely relative to f of n, where E of t sub n equals f of n times the energy at t sub n minus 1 to the power of 1 plus alpha I plus h of n, where f of n equals beta to the power of n direct scaling, and h of n equals 1 over f of n inverse scaling, are fractal scaling factors for energy, and alpha y incorporates an imaginary component related to the tachyon's hypothetical nature. Fractalplicitive spatial displacement equation with inverse influence. The spatial displacement S of the tachyon is governed by a recursive relation that incorporates both direct and inverse fractal scaling, defined as S of t sub n equals S of t sub n minus 1 times 1 plus f of n times e to the power of alpha I t sub n minus h of n times S of t sub n minus 1, where h of n equals 1 over f of n, serving as an inverse scaling factor that counterbalances f of n, reflecting the concept of fractalplicitive inverse theory. Implication: if a particle or disturbance exhibits energy and spatial displacement patterns that conform to these recursive, fractalplicitive direct and inverse scaling relations across fractalplicitive time intervals, then it may be identified as a tachyon. The detection relies on identifying a unique signature self-similar recursive patterns in energy and spacetime displacement that display both amplification through f of n and diminishment through h of n. Fractalplicitive inverse theory's role. The inverse scaling factors h of n equals 1 over f of n ensure that the tachyon's influence on energy and spatial displacement oscillates between amplification and reduction. This oscillatory pattern is hypothesized to be a unique marker of a tachyon, distinguishing it from other particles. Under fractalplicitive inverse theory, the combination of direct and inverse fractal scaling patterns results in a recursive fluctuation between amplification and diminishment of energy and spatial displacement. These patterns, if observed, would be characteristic of a tachyonic particle or similar superluminal phenomena. Detection would involve confirming this alternating fractal behavior in experimental measurements. Corollary: the detection of both direct and inverse fractalplicitive patterns in energy and displacement would serve as empirical evidence of superluminal or faster-than-light phenomena, potentially validating the existence of tachyons or tachyon-like entities. QED, quod erat demonstrandum. This theorem establishes a novel, theoretically grounded approach for tachyon detection based on fractalplicitive scaling principles. It posits that a particle exhibiting both fractal amplification and inverse scaling patterns in energy and spatial displacement across recursive fractalplicitive time intervals would indicate the unique properties of a tachyon or tachyon-like entity. By incorporating fractalplicitive time theory and fractalplicitive inverse theory, the theorem provides a framework that captures the hypothetical oscillatory and self-similar behavior expected of tachyons. The alternating scaling, amplification through f of n and reduction through h of n equals 1 over f of n, produces a unique signal that distinguishes such superluminal particles from conventional subluminal matter. Summary of detection criterion. If a detection apparatus can identify energy and spatial displacement patterns with 1. Recursive, nonlinear time intervals governed by Fractalplicitive time theory, 2. Self-similar energy scaling alternating between amplification and reduction according to Fractalplicitive and inverse scaling factors, f of n and h of n equals 1 over f of n. 3. Oscillatory spatial displacement demonstrating recursive fractal behavior across intervals. Then the observed data may confirm the existence of a tachyon, thereby providing evidence of faster-than-light particles. This theorem represents a speculative but mathematically consistent approach to studying the properties of hypothetical particles within a fractalplicitive framework. Though further theoretical and experimental validation would be needed, the theorem lays a foundation for future research in superluminal physics and particle detection methodologies. Conclusion: the theorem of Fractalplicitive Tachyon Detection with Fractalplicitive Inverse Theory proposes that the presence of a tachyon can be detected by observing unique, recursive fractal patterns in both energy and spatial displacement over fractalplicitive time intervals. This detection relies on identifying alternating scaling behavior, direct amplification through a fractalplicitive scaling factor f of n, and inverse diminishment through h of n equals 1 over f of n. These oscillating patterns are unique to tachyons, which are hypothesized to exhibit faster-than-light properties and distinct oscillations due to their imaginary or complex valued mass. In this theoretical framework, Fractalplicitive time theory modifies the time intervals t sub n to progress in a non-linear fractal manner, reflecting the tachyon's effect on time. Fractalplicitive scaling introduces self-similar recursive changes in energy and displacement. Fractalplicitive inverse theory adds the necessary counterbalance by introducing an inverse scaling component, resulting in a unique pattern of alternating amplification and reduction. Implication for experimental detection. To detect a tachyon using this theorem, an experimental apparatus would need to be capable of measuring energy and spatial displacement in recursive fractalplicitive time intervals. Detecting both the direct and inverse scaling effects would signal the self-similar alternating patterns characteristic of a tachyonic entity. The ability to identify such a fractalplicitive signature could ultimately lead to empirical evidence of tachyons or other exotic particles that exhibit superluminal characteristics.